Finding linear transformation matrix. Okay, so how do we find the unknown when we're only given geometry or something quantitative? So in 2D, this is actually quite nice. This is a very interesting thing to remember. That was a terrible star. Pretend this is a star, okay? So basically, any transformation matrix T can be expressed as T of 1, 0 and T of 0, 1. Like this, okay? In 2D. In 3D, exactly the same. T in 3D. So the whole matrix, T of 1, 0, 0, T of 0, 1, 0, and T of 0, 0, 1. This defines the transformation matrix. So what we call 1, 0, and 0, 1, we call these the axes vectors because they'll be along the axis, right? Unit vectors on the axes. That's not something you have to know, but there is a name for it, which I think is interesting to think about because it actually has a quantitative meaning. But the general method, we find the transformation of the principal vectors E1, E2, En. So with the axes vectors, as I call them, and by definition of transformation or geometric operation as these, then we can formulate them to look like this, which is what I've written here and above over there somewhere. So that's a lot of words. Let's actually put this into practice and see what this actually means. So we're gonna start here. So on this question, give me a moment. Find the corresponding matrix M for linear transformation of this to that. Okay, so again, as I said, the T matrix is just a formulation of T of 1, 0, 0. Well, in this case, it's 3D because we have X, Y, and Z, right? Just by inspection, X, Y, Z. T of 0, 1, 0. And T of 0, 0, 1. Okay, so let's write this out actually. So we have T of X, Y, Z equals to X minus Y, 3Y, and 3X plus 2Z. Okay, so let's look at this guy first. We're going to sub in 1, 0, 0 for these. Okay, so X equals 1, Y equals 0, Z equals 0. So then we get T of 1, 0, 0 equals, so X is 1, Y is 0, so 1. Y is 0, so 0. X is 1, Z is 0, so 3. We do the same for T equals 0, 1, 0, okay? So in this case, X equals 0, Y equals 1, Z equals 0. And we get, let's see, -1, 3, and that is 0, I believe. Let's see. Good. And give myself some more room here. X, T of 0, 0, 1, Y equals 0, Z equals 1. We get 0, 0, and 2. Okay, so now we put this into, this, right? So T, I like to have a squiggly here to indicate matrices. So like just for your reference, a squiggly means it's a matrix. I might write this down occasionally. And X with a line underneath is a vector. It's just my convention, just to not confuse myself. But anyways, so T equals T1, 0, 0 is on the leftmost column, right? So remind ourselves 1, 0, 3. T of 0, 1, 0 is in the middle, which is -1, 3, 0. And finally, on the rightmost column, 0, 0, 1, we have 0, 0, 2. So just to be extremely clear about this, this is T of 0, 0, 1. This is T of 0, 1, 0. And this is T of 1, 0, 0. All right, let's take a look at your questions. Would it matter which order R and RT are in? I don't think so. I do not think so. No, I don't think so. I'll have to confirm with you on that later, though. I'll get back to you on that, but my gut tells me it doesn't matter right now. Okay. Nice, straightforward, huh? Next one. Linear transformation r squared rotates 45 degrees and reflects it through y equals 0. Okay, so so step 1. Let's just find the point of p naught 1, 0. Some random point 1, 0, okay? Because we want transformation of 1, 0 and transformation of 0, 1, right? Because that's going to formulate the overall t, right? Because this equals t. This is always going to be true. It's just something to remind ourselves of, okay? I should just erase this. Okay, so we know our first transformation is going to be a rotation vector, right? So let's just focus on this guy first, okay? So we're going to do 1, 0. So we apply a rotation vector, rotation of 45 degrees. I'm not going to write the whole matrix here just because I need to save a bit of time here. But if you do the proper matrix multiplication, you get cos 45 and sine 45. Okay. And now we're going to reflect it through y equals 0. So, y equals 0 is this line here. Theta equals 0, right? So reflect 0, cos 45 and sine 45 gives you cos 45 and negative sine 45. Good. So this is equal to t of 1, 0. Do the same to, we'll call it 0, 1 now. So again, rotation 45 degrees onto 0, 1 equals to, this will give us negative cos 45 and sine 45. And then we reapply the reflection again to this one now, cos 45, sine 45. And we get negative cos and negative sine. Okay, so this is equal to t of 0, 1. All right, now we put these guys together, put these two together. So remind ourselves t equals t of 1, 0, t of 0, 1. And that will give us 1 over square root 2, negative 1 over square root 2, negative 1 over square root 2, and negative 1 over square root 2. Okay, let's take a look. Please scroll up to A. I will scroll up to A in a second. Right now. This one? I'll let you write it down. How did you do the reflection? Okay, so the reflection, we are told it is against y equals 0, right? So we know that's a horizontal line. So if you flip back to the page that showed you graphically what's going on in reflection, you'll see that if it's a horizontal line, our angle is actually 0. So you plug in 0 for theta in the reflection matrix. And I skipped the math here, but basically I have a reflection of 0 multiplying to something after I've rotated it already. So then that's how I did the reflection there.